talk to us about what is Sage Math good for. William was a student of Hendrik Lenstra at Berkeley, and then he went on to be a Benjamin Pierce Fellow at Harvard, and then be a professor at UCSD, and then a professor at University of Washington. And now he is the CEO and founder of Sage Math. He created Sage Math 11 years ago. That's probably so yeah, he's going to tell us a bit about what has happened since then and what you can do with Sage now.
Thanks.
I don't know, maybe I'm supposed to hug you.
Fist bump.
Fist bump, yeah. Okay.
Am I supposed to wear this longer?
Yes. Yes.
Yes or no? It's kind of distracting. I'll try. If I get annoyed, it's coming off. It's kind of
But it should lay
poking me.
Oh, yeah.
Oh, you like that?
There you go.
Okay, got it. Sorry. All right, so I'm going to talk about what Sage Math is, where it came from, and some of the things it's good for, like why you might want to use it. So first, what is Sage Math? So just a little background where it comes from. In the 90s, when I was a grad student of Hendrik Lenstra at Berkeley, I wrote a C++ library and command line interface for something called Pekka, which was a program for computing modular forms. So you put in some information about some modular forms you want, and then wait, and it would output the modular forms. It was extremely useful, but it was kind of its own little, program that was isolated from other things. And I ended up spending a lot of time writing an interpreter interface, like a way to type questions into the program and get output and to use it. It's kind of like an adventure game where you're writing a little, way of interacting with the program. And thought it would be nice to instead take the same sort of algorithms and implement them in a bigger system so I could take advantage of things that were already there. And I found out from another grad student about Magma, which is a closed source for money piece of software that's developed, mainly funded by grants maybe at the University of Sydney in Australia. And it had one feature that made it extremely useful for modular forms computations, which is that it's extraordinarily good at exact linear algebra. That is, doing linear algebra where the entries are not rounded. You don't round off. There's no round off error. You're working with rational numbers, numbers in a finite field, etc. It has amazingly good algorithms for that, and that's really kind of a critical input to modular forms computations. So I rewrote over 3 separate visits to Sydney, Australia, a lot of my code to run as part of Magma. So if you type Magma modular forms into Google, you'll probably find the reference manual for Magma's page on modular forms. You should at least. Maybe you don't. But if you did, then you would see that there's a lot of code there for computing with these objects. And that's what I did in the late 90s. But I was kind of frustrated with some aspects of Magma. I looked at my computer in around 2003, and the only thing on my computer that wasn't free and open source software was Magma. Magma being really the only program I actually cared about. So it's kind of ironic that out of everything I used, the one thing that mattered the most was closed source. So unlike, say, my web browser or LaTeX or whatever, all that stuff's open source, but then Magma is closed. That was frustrating. And there are other problems, which I won't go into. So in 2004, I started writing an open source alternative to Magma, primarily designed, the initial goal was create an open source alternative to Magma for my research, which is a pretty, well, I'm not going to say my research is really narrow, but it's a fairly limited scope. And so I tried to get other people interested in helping me and working on this, and for quite a while I couldn't get anyone. So there was one other grad student at Harvard at the time. I was a BP, or assistant professor at Harvard, and he was really, really interested in programming and mathematics. And when I told him what I was doing, what I was building, he's like, "So what new algorithms that have never been implemented before are you implementing?" And I was like, "None. I just want something that will actually be useful." And he didn't want to work on the thing at all, just because it didn't involve implementing or creating new algorithms that had never been implemented before. So it's kind of boring to a lot of people to just try to make something that re-implements but open source things. So I did that, and I made a public release. The very first user, David Joyner, wasn't a number theorist, he was a coding theorist. And so I had to expand the scope of the project some to get at least somebody else involved. But I got him involved, and David Cole as well, another actual number theorist who had worked a lot on Magma. So in any case, a little over 10 years ago, I made the first public release. And a kind of what is Sage answer, especially back then, is it's what you get if you take the best of some open source software, like a programming language, a library for number theory, a library for linear algebra, etc., and put them together and then add some stuff on top to compute modular forms. So that was kind of what it was at that point in time. But it started getting a lot broader very quickly. We came up with a new mission statement in 2006, which is much better at attracting a wider range of people. So the mission statement is to create a viable, free, open source alternative to Magma, Maple, Mathematica, and MATLAB. And that tells you something about the scope. If somebody says Mathematica can evaluate blah easily, then Sage should have that functionality. If somebody wants you to add something that has nothing to do with any of those programs, you might question it, possibly, depending on, at least it sort of sets the range. And then over the last 10 years, there have been over 500 contributors. So there's a lot of code that's included in the Sage distribution when you download it, install Sage, or use it that we didn't write. There's also a lot of code that Sage developers, that mathematicians wrote, the people in this room. And there have been over 500 such people, around 1 million lines of code written, and there's so it's really hard to answer questions like how many active users does Sage have? But what is easy to answer is how many active users does the website have? How many people visit the website every month? And that's on the order of 50,000, because every time somebody visits the website, you see that. And so that's some function of hopefully a roughly linear function of the number of actual users. Because if somebody uses Sage, they might go to the website every once in a while to see what's new or to look for documentation or something. So that gives a sense of the usage. How many people here have ever used Sage, even once? So like 80%, well over half. So that's good. That might be reflective. There's my sample of the general mathematical community. 50,000, of course. I don't know, maybe there are 50,000 mathematicians in the whole world. I don't know. There's a lot more than 50,000 potential Sage users. Because if you think of your undergrads and calculus classes across the country, there's probably 1 million undergrads who take calculus each year. And many of those could use Sage. Okay, so next, what is Sage Math Cloud? So Sage Math is a piece of free open source software. It's very big and complicated, and it's meant to be an alternative to Mathematica, Maple, MATLAB, etc. Okay. Next, there's Sage Math Cloud. So in 2012, I was invited to this exciting meeting at the Simons Foundation's headquarters in New York City, and sort of they asked us in the letter, think big. What would we do if we had on the order of $10 million to support the development of open source software in math and physics? And you have this meeting coming up, you think about it for weeks and months beforehand, you start coming up with plans, you think, wow, if we had that kind of money, think of the amazing things we could do. So I started dreaming again about doing really big stuff, and then they concluded at the meeting that they would fund Magma. So that motivated me to maybe try a different funding source than the Simons Foundation for Sage development. So, I invite you to imagine what you might do if you had a few $1 million a year to support the development of open source math-related software. Maybe you would spend it on some grad students who are doing somewhat computational things. They could be supported by that money. They would contribute to the software instead of teaching calculus sometimes. That sort of thing would be fantastic. Or maybe you like programming a lot, and one semester, instead of teaching, you get bought out of your teaching, and you instead write a bunch of code for Sage. So that's the sort of hope that I eventually dream of being able to support. And that's, by the way, more or less what Magma does already, though they typically have the people come down to Sydney to work for them. But it's pretty similar. And we've been doing that for a long time. So in 2013, I launched Sage Math Cloud. What it is a collaborative web-based interface really all the open source software that I use in teaching a course on open source math software, and that I use when writing research papers. So you can think of it as that. The motivation or connection with the previous one is that as Sage Math Cloud is a website, and when you use it, you sign up, use the website, maybe some people will want to pay to have like more powerful compute ability in that website. So there's a potential business model related to making this other open source software available via a web browser rather than just something that people download. So that's the idea. That's the connection with the dreaming about actually having money. And I've taught, I don't know, probably a dozen times over the years a course on Sage and LaTeX, just kind of general open source software to like 30 to 60 undergrads. So you start seeing it would be really good to have a week on how to use LaTeX. It would be really good to talk about Python, all these other things. But if you try to make the students all install LaTeX or Python, it can get really ugly. So instead, it would be nice if they could all do everything they need for their class just by going to a website. And that was the idea and the goal here. And then I wrote it, tested it out multiple times in classes. And now, right now, there's a company I started last year, and there are a couple of people working on this Sage Math Cloud website, and there are nearly 1,000 paying customers, and then also in addition to that many active users who are not paying customers. So it's a freemium model. People can use the website entirely for free, but if you pay, there are some benefits to doing so. There are a lot of people like in third world or developing countries that don't need the benefits of paying, and they're really happy that you have this free service so that you just do everything. And there are other people for which the amount you pay, which is between about $4 to $9 per student per semester, really isn't that much given how much the students are paying. And so they're happy with having the students pay. And they value what they get for that. Okay, so the rest of the talk, what I'm going to do is tell you first a little bit about teaching a course that involves computation, so a little more detail about how that would work using Sage Math Cloud. Then I'll talk about writing papers, both assisted by Sage Math and Sage Math Cloud, so how it might change or improve how you write a research paper. Certainly it has for me. And then I'll talk about a little more about what Sage itself is really good at, or some of the things Sage can help you with if you're doing computational research. So for example, if you have an algorithm that you want to implement and have peer-reviewed and also maintained indefinitely, which is something journals just don't do, Sage provides very, very polished in a sense that has been done a lot process for doing that. Not in the sense that it's necessarily smooth, but definitely polished in the sense it's been done a lot. So that's an outline of what I'll talk about. Maybe I'll zoom out a little. So I think if you want to teach a course that will involve, say, LaTeX, or not necessarily writing LaTeX files, but maybe writing a file that has lots of LaTeX formulas in it, or you want the students to use R or Python or C or some sort of language like that, and you want like zero friction. They just log in using a web browser to a website, and they get all the software that they'll need for the course without having to install anything. Then Sage Math Cloud, and in particular, if Sage, this very big piece of software I mentioned before, is one of the things you want to have. It'll all be pre-installed and available for them, with every optional package you can imagine too. And not only that, since we've been running it for 3 years, and it's been used now by over 200 courses, people will request additional packages to be installed, and then when they notice that they're not there, and then we've installed them, and over time the number of requests goes down a lot because we've pretty much hit most of the things that are needed. Okay, so there's course management. You can create a project. What you do is you create a project in Sage Math Cloud. Let me just show it to you for a second. So you see what it looks like. It's full screen. Okay, so here's Sage Math Cloud. It's this website that I'm bringing up right now. So here's the Sage Math Cloud website. When you load it, you see if it's the first time you've ever used it, you'll probably see a list of no projects. But I have, of course, many projects. And in here, there's a workshop going on, Sage Days 81, right here. And we have a project associated to that workshop. And as you can see, there are a bunch of files in a web browser. So from a technical point of view, what SageMath Cloud does is make it really easy to have lots of Linux accounts sort of in the cloud remotely that you can use through a web browser collaboratively with other people, like students in your classes. And it has course management functionality and just lots and lots of stuff pre-installed in it. And just to do a quick little demo of that, if I go to people and my name, I'm going to make a course. So I click on manage a course, and then I get this thing which I can then, I can add students to the course. So I'll add some other student I made up, some test account. So you can just paste in a list of students there, and then you'll get one little entry for each of the students. There's automatically another account set up for that student, and you can push out assignments to the students. An assignment is just an arbitrary directory of files. You can put whatever you want in that directory. It could be a text file, it could be a Python script, or an R script, or a Sage worksheet, or a Jupyter notebook, or whatever. You push it out to the students work on it. While they're working on it, you can see exactly what they're doing. Every single student, you know when they're working, you know what they're doing. They can like type something on the side and ask for help, and you'll get a little notification. You click on it, and then you'll see in real time, as they're working on their assignment, what they're doing wrong, and you can make a comment suggesting what they might do to fix it, or you can just jump in and fix it if you want. So for example, this person that I just added as a test student, they have their own project in here, and I just clicked on it, and it's hopefully going to open up. But while they're working, you can sort of help them out and chat with them and so on. So just wanted to show you that for a second. Now I'll switch back here. So the experience is that the students can do everything technical, like running Sage, everything using LaTeX, etc., all through their web browser, which students are pretty comfortable with nowadays. There's also some other nice features, like when you're editing a document, it records every version of the document as you go, about every 2 seconds. And there's a little slider, and you can drag it back and forth and see all the previous versions. So there's this like complete log of exactly how you got to a given place. And this is good because you'll have figured, as a student maybe you'll have figured something out, and then you break it, and you can always drag the slider and see what it was before you broke it and copy and paste it back. And it kind of eliminates the my dog ate my homework problem. Or the wind blew away my homework, if they're working outside. So this system that we have developed has been used by hundreds of courses. That link has a list of them. So I'll click on it. So here's a list of classes. It's pretty long. Let's see, and look at apparently the very top one is Aaron's just sent out the invites in for this. He's teaching a calculus class in Hilo. And he's been teaching using SageMath Cloud. He wants his students to be able to use Sage for the labs, and he doesn't want them to install Sage or go to a computer lab where Sage is installed. And he's been using it since 2013 repeatedly, many years. And we've talked back and forth a lot to help develop some of the pricing models and stuff that would work for his students. So he helped me design that. And also another thing is, this isn't just some website where you can't get any help and it's just sort of thrown out there. Especially if you're a paying customer, you're professionally supported. So while you're using the website, there's a little button you can just click right here, help. You click it, you type something, and then a support ticket gets created. And then people who are extremely good at understanding Sage and other open source issues and LaTeX issues will see your ticket, and then they get direct access to the problem you're having, so they can see the file that you messed up and how to fix it and so on. Those people are, of course, just me and Carl right now. But I assure you, we know Sage really well in LaTeX and stuff, so it's a really good quality support, and there'll be more people involved soon. Hello. And yeah. I'll skip that. Okay, so that's second section. Okay, the next section is about collaboratively writing math papers. So, of course, many of you have written papers using LaTeX with co-authors, and it's fun. Like the old way to do it is somebody says, "I will write the paper for the next 3 days," and then when they're done, they give it to you, and then you say, "Okay, I'll write the paper for a few days." You just kind of do like a tag team thing. That's typically what people have done in the past, and it's a decent way to work because then, like when you're you really feel like you should do something. But another approach to writing a research paper is that you can do it inside of Sage Math Cloud. And before going through some of the benefits of doing this, I'll just show you what it looks like. Oop, that's not good. Okay, so I'm going to create a LaTeX document. So I'll just call it my paper LaTeX document. And what this does, if you look over here, is there's now a new file, mypaper.tech. There's some other auxiliary files that you probably don't want to look at. That's why they're in gray. And there's a PDF file that gets created. And on the left, you have the LaTeX document that you can edit, and on the right, you have the rendered version of it. And then you can make some changes. And what happens is anytime you save the document, it will run LaTeX and then update the output. And you can also click like this button right here, and it gives you the PDF. And you can double click on anything on the right-hand side, and it will take you to the corresponding point on the left-hand side. So it's not so useful for a tiny document, but if I double click on consider, then it takes me to consider. So you have that like forward and backwards. And it works in both directions. Like if I click, if it's here and I click forward, then it highlights, it goes to the appropriate page and highlights it. So it's a nice editor. By the way, I mentioned the time travel where everything you do is recorded. So if you click time travel, you can go back and forth. There's a little slider, and it shows the document as it evolved over time. So that can be useful. And it also says who did what. So Harold is right there. Just type something. Notice that you can see his cursor and his name. Maybe could you do something with multiple cursors? Or? Yeah. Okay. So notice he has 2 cursors. So you can, like if you want to comment out a couple of lines, you can just do that. Or so. Okay. So it's kind of nice things about the editor that you use. You can also split the screen vertically or horizontally. So notice this. What I'm doing here is I'm showing you 2 different points in the document at once. So maybe you want to look at the preamble, but at the same time you want to look down here. So you can do that sort of thing. Little convenience things. What? The chat bar. Oh, yeah. Over here there's a chat. So which you can use math in here. So you can type like a formula like this, and then it'll typeset it. It's nice. And if you make a mistake like that, so that's not, I don't think there's a \foo in LaTeX. Notice it says issues, and there's a button, and then it tells you what the mistakes are. So it's like a LaTeX editor, but it's collaborative. But what makes it more powerful than any of the other web-based versions is that in addition to all this, you have direct access to all your files. You can put anything there, any data and computations that you want to incorporate into the LaTeX document, etc. You can also create a terminal, which I'll show you in a second. And that lets you, via the command line, do whatever you would normally do. Command line takes a second the first time. Okay, so this is a terminal. You can just directly type LaTeX if you want. And notice there's the error. We can continue. So it's really like you're using a traditional Linux computer under the hood. Except notice this is all in my web browser. And it's collaborative. He can open the terminal and do stuff as well. And he can also see what I'm doing. So if you're collaborating with somebody else and you suck at using the terminal, but they're really good at it, then you can benefit from that. Moreover, things like Sage are installed, of course, here. And one of the nice packages or one of the nice things that Sage itself provides is a package called Sage Tech. It lets you embed calculations using Sage in LaTeX documents, and the calculations get evaluated the first time they're seen and then cached. So unless you change the input, so you can have a bit of code like he's writing right there. I'll also write something. This year is 2016, which equals, and you could say something like factor 2016, like that. You can still have that foo mistake, so that's probably causing trouble. And what it'll do is it'll evaluate the Sage code, figure out what the corresponding LaTeX representation is, and then display that in line. So as soon as this finishes, it should show us, look, so I don't know if you can see right here, but I'll zoom in. So I didn't have to like figure out what the factorization is, copy and paste it from another thing, all that sort of stuff. I just did it automatically. And it's in fact very sophisticated. Sage Tech was started at Sage Days 1 in 2016, which at the time was called Sage Days 2016, because I thought there would be at most one per year. The one that we're having right now in Honolulu is Sage Days 81, which is maybe the 85th Sage Days. So we've had a lot of them in the last 10 years, a lot more than one per year. But Sage Tech started then, and it's pretty polished by now. There's quite a lot you can do, like draw graphics and have blocks of code and all kinds of other things. People often use it like for automatically making homework assignments and stuff like that, where you can, generate matrices with certain properties or functions with certain properties, and then maybe integrate them or differentiate them. Okay, so now back to this, or back to the talk. And well, just to emphasize, these are all just files. This is a terminal. You could use Git or any other thing or you can use Git, for example, to commit these files to a local repo, push them to GitHub if you're collaborating with somebody using Git or some other tool like that. So you can use a lot of your standard workflows that you might be familiar with if you're a command line Unixy person. You don't have to. Many people use Sage Math Cloud, never ever open a terminal. Okay, so now back to this. So just to summarize, when you collaboratively work with LaTeX documents, you can use Sage Tech. You have the slider that lets you go back and forth in time, multiple cursors. One thing is we did a big survey of Sage Math Cloud users, and a lot of people said that they want us to improve the LaTeX editor. So I don't think that means it's bad. It's just that it means we're going to put a lot more effort into it soon. That's what it means. That's the implication you should take away. And also that it's a popular reason people use Sage Math Cloud. Okay, next. So this is now going back to the core Sage software and telling you about something useful. Something I haven't mentioned yet. Sage Math Cloud, it's a website, we run it on Google Compute Engine. The source code of it, though, is 100% open source and free. So if you want to have your own Sage Math Cloud, that's something you can do. Just wanted to mention that. Okay, so another thing that you can do is if you write a bunch of code for your thesis or for a paper or something, and you want it to, maybe it's really hard work to write the code, and you really wish somebody else would actually look at it and carefully go through it, and maybe you wish that the code will still be usable in 10 years when you're maybe not thinking about it anymore, and if you kind of want it to work on OS X and Linux and other operating systems, you can contribute it to Sage. The process of contributing code to Sage is documented in the Sage Developers Guide. I'll click on the link. Oops, this went out of my talk. So this is just, it's a document, it tells you what to do. The quick summary, though, is you create a ticket on this server called Track, and I'll show you that in a second. You write some code according to our standards and guidelines, and as I mentioned in parentheses, writing and pushing the code can be pretty hard. Writing code is very hard often. And you put your code there, and then you set the ticket to needs review. And then somebody else, maybe multiple people, will carefully look through your code, read it, make sure it makes sense, make sure that it's sufficiently documented, that there are enough tests of the code, examples, etc. We have a list of criteria, that's what's linked to right there. And then the code will go into the next release of Sage. Once it's in Sage, we build test on a very large number of different machines. Lots of people download and install and build Sage. Inside of Sage itself, there are many hundreds of thousands of automated tests. So these are all getting run. And Sage has to support 32-bit, 64-bit computers, OS 10, Linux, and I think we maybe test on Solaris still, I can't remember, etc. So your code will get sort of more widely tested and continue to live. Like if your code suddenly, the tests start breaking because of something somebody else changed elsewhere, or just because Apple releases a new compiler that changes things, we won't be able to release a new version of Sage until we fix that. And so it sort of ensures some life to your code. It's very different than a journal lets you, put a source code listing as an appendix to your paper. I mean, that's really not so valuable because will it work next year? So that's something that Sage provides. And let's look at Trac for a second. This is the site I mentioned. So you can see there's a list of people if you go way down here. These are all people who have accounts on Trac. It's kind of a tedious process to get one, unfortunately. You have to email a list and then wait and explain yourself so you're not a spammer. Probably. So, it's not, these aren't just a bunch of random people that didn't do some Sage development. Most of them have contributed to Sage in a significant way. There's also, there's a timeline which shows you what's going on. And you can see from the number that a lot has, this is yesterday's timelines. These are actions that happened on various tickets. So there's a lot of stuff going on here. One of the interesting things that really distinguishes how Sage, how sort of publishing your code in Sage is different than publishing in a journal, is that the refereeing process is public. So just to give you an example of that, here's a ticket. So this was a Google Summer of Code project by a grad student of mine a few years ago. By the way, if you don't know about it, Google has something called Google Summer of Code, which will pay a student to work on writing open source software all summer. It pays minimum wage, literally. Actually less than minimum wage in Seattle, but it's a good experience, and it's really nice that Google does this, and it's a good way to support contributions to Sage. We typically have about 5 students paid by Google to work on Sage during the summer. So this was his project, and here's his ticket. He says this ticket involves something called analytic rank bounds. So it's a technique for getting information about elliptic curves. It is pretty important, and it uses the Riemann hypothesis, basically. So there's a bunch of discussion about the ticket and state changing and questions and maybe issues. And there's discussions about numerical noise involving testing, but it's all public and you can tell what it means. It goes on for quite a while. This ticket gets changed to positive review at this point by me. I rubber stamp it. But then somebody else tests it and he says, nope. On 32-bit Linux, which I didn't even bother to test on, because who has a 32-bit Linux computer anymore? The last digit of the digamma function at 3.2 is different. So it's wrong. Our test suite has a huge amount of tests like this, and it really tests the output is correct, is what we claim. See, it's not quite right. There's some funny business with the last few digits, and so he changes it from positive review back to not positive review. Needs work. And then I found some other issue somewhere else, and then he explains what's going on. The point is that, unlike when you referee a paper or when you have a paper refereed, it's public here. So it's just different. I think it's important, though, because if you submit something to Sage and then you, say, list it on your CV and you want it to have any meaning at all, from the point of view of somebody maybe trying to hire you, at least you can tell them there's a website where they can go and see exactly what lines you submitted to Sage, and exactly that it was actually peer-reviewed. Does that have any value? I don't know. But at least it's well-defined. We like well-defined stuff. Like if you say you submit a paper to a journal, how to say what that even means, that it was accepted. Because it could be a really sloppy reviewer. Maybe the paper's wrong. With Sage, at least, you can see that the reviewer is really sloppy or not. Because you can see all the discussion. Here's my discussion after 14 months. So it is kind of like math journals. He finished it, and then 14 months later, I commented that this still hasn't gotten to Sage, Mr. Cussy, et cetera, by other people. So sometimes the time span can be similar to papers in math journals. And then there's other people, blah, blah, blah. Anyways, the point is it's public. It's also different in that it's really open. Like when you contribute code to Sage, it just is freely available to everybody forever under the terms of the GNU public license. And we don't charge you to contribute code to Sage, like journals charging people open access fees or anything like that. Okay, now the last section is about exploring new mathematics and how Sage is useful. So Sage has, at this point, at the beginning didn't, but now it has an enormous range of functionality that's relevant to research mathematics. It also has lots of things that are relevant to teaching calculus, graph theory type stuff, and basic proofs. But it does have a lot that's motivated by research math. And most people that work on Sage or contribute to Sage are pure math researchers. So that's where we are particularly strong. Also, it has a lot of numerical and applied functionality. The reason is because Sage is technically what it really is it's a very large Python library and distribution of software. And anything that's being written that's usable from Python is automatically usable from Sage. And we make sure that a certain subset of all that stuff is available in Sage, in any copy of Sage. So we include it and test it. And a lot of people use Python, and there's like a whole ecosystem of numerical computing functionality in Python. And so Sage benefits from that automatically. And in fact, there are a lot more people working on that ecosystem than the people working on Sage. So purely by virtue of choosing Python as our environment and language, rather than inventing our own language, we benefit immediately from that whole ecosystem. So there's really a lot of stuff for numerical applied computation in Sage. Of course, there's a lot of number theory because many of the people involved in Sage are number theorists. Algebraic combinatorics is extremely strong in Sage. One of the reasons is there's this really organized group of people who had a project called MuPad Combinat, where they had worked to put just massive amounts of code related to combinatorics into MuPad. I don't know, has anyone here ever even heard of MuPad? One person. There you are. So MuPad isn't super well known. It doesn't really exist anymore, but it was originally in the 90s something funded by the German government, and then it became a private company. And then I remember talking to their lead developer at a joint math meeting in like 2009, and the only thing he said to me is, "We will survive," with a strong German accent. And then like a year or two later, MATLAB bought them and incorporated them as some. I think they somehow made it as it was somehow part of their symbolic toolbox option. So it went from being free for all the people working on the MuPad Combinat project to, and not that expensive for other people, to how much MATLAB add-ons cost. They're really scary expensive. So it got very expensive. So they fortunately decided to rewrite everything they had done and more on top of Sage. So they spent many years doing that. And I think they're done at this point. Now they're writing lots of new stuff. Interestingly, their work to do that started with an undergraduate at Harvey Mudd in 2007 deciding to do the same thing before they did. And he did like a third to a half of it, this guy Mike Hansen, who just sort of systematically went through and did a huge amount of rewrite of their code in Sage. He liked programming Python and Sage. So algebraic combinatorics is really, really nice in Sage. We have lots and lots of graph theory. It was pretty good in 2008, and then it's just been polished ever since. As I mentioned before, exact linear algebra is very important in number theory and many, many other algorithms. Some people, a lot of math is about reducing things to linear algebra, right? So even in computational math, a lot of it is about reducing things to linear algebra. So it's important that linear algebra be fast. So we have pretty good linear algebra. And recently, this is very recent, we have a lot of geometry and topology functionality that wasn't there a year ago, but has been developed and is now in Sage. There is a reference manual. And here it is. This gives you kind of a top-level view of what's in Sage. So there's a part that's number theory and algebraic geometry. There's a part called geometry and topology, probability and statistics, discrete math, etc. Calculus. So you can click on one of these things and then see something. I'll click on 2D graphics. Our plotting also, it's not, I mean, it's actually pretty good, I think. So 2D plotting, I don't know what to click on. Okay, complex plots. Ooh, so you can give a function and it'll draw a complex plot. That's kind of a nice thing to have. Actually, I'll do a live demo of this very thing. So I'll go over to the project where we're playing. Oh, thank you. Oh, in Santi test. Okay. Let's see. If you want to see, I don't think you did. I don't see any worksheets. Oh, I see it. Duh, I'm just maybe. Okay, so worksheet.sagews. So open that. Great. So he's here for me. And by the way, if you're teaching a class and you're using a worksheet live to demo things and to talk, and you have a TA, then often you can have them do stuff and you can talk, or like you make a mistake and they'll fix it or whatever. So yeah. Like here, maybe you do that, and then your TA would be, oh, he or she would quickly do that, and it suddenly works. So. And similarly, I guess, I'll do a 3D plot also. So I'll do like oh, you already did? Okay, thank you. So, here we are. So there's a little 3D plot. Remember, this is all in my web browser. It would look the same like on a phone. It's collaborative. There's a history of everything that happened for all documents in SMC. So like, if you wonder how did you do all this, there's a little slider and we can watch as the worksheet is sort of created. So for example, it recorded the little mistake with that, and then fix. Oh, no, I mean, oh yeah, one back, or yeah. So there it's broken, and then you can see that a minute later it was fixed, and then we evaluated it, so on. Okay, so, but I don't know. Let's look at another one. So let's say geometry and topology. I feel like there's probably a topologist or geometer. Or any geometer? Okay, cool. So look, there's things like knot theory and combinatorial geometry and differential forms. So you're probably happy to see that. Manifolds, parametrized surfaces. So there's some logic stuff. So symbolic logic is like you're teaching a first course of proofs. It's that kind of symbolic logic. It'll generate truth tables and stuff like that. SAT solvers is a different type of logic. So it's like for solving serious problems. Okay, so I think that, if there's anything else I want to say. Oh, there's a little bit. Okay, so one point that I want to make is remember to see when we clicked on the documentation for plots, there were a lot of examples. Let's say we click on the documentation for differential forms, which I've never even looked at. I am, was it lower? Okay. I am confident that there's going to be an example when I get to one of these sections. So, say elements of the algebra. See, there are examples. And the reason I'm confident is because we had a conference at Sage Days a long time ago where there's a bunch of argument. We decided that any code that goes into Sage, every single function, even private functions, must have examples illustrating the usage. 100% of them. And we also wrote a bunch of tests, or things to tell what the coverage is. So basically, anytime you look at any function anywhere in Sage, at least with 95.7% chance, you will find that there's an example illustrating its usage. Moreover, the example will actually work. That's the amazing thing. Like, if I take this code, which I've never seen before in my life, and I go over to that worksheet, and that is a good point. Let me run it in the current version of Sage. Thank you for warning me before my magic trick did not work. So I'm just pasting that code. Oh, and maybe I didn't copy it. Well, I'll tell you what I'm doing. So that creates 3 symbolic variables, so you could do things like that. Okay. Kind of boring, but then you could do expand. Sage, by the way, you can use it both via a worksheet mode or via the command line or via Jupyter Notebooks, which is another kind of worksheet style mode, or from within a LaTeX document. So there's a lot of different ways of using Sage, and also via Python code. You can use it as a Python library. Okay. It's why is it suddenly? Okay, so far it's working. There, so that's pretty cool. We've created this differential form. And the point is that there are hundreds of thousands of these examples now, and they actually work. So when you're trying to learn how to use, wow, cool. In the terminal, you get completions that pop up. That's pretty neat. So we made a differential form, and then you can ask the question, what can you do with a differential form? And what you do is you type the object that you have, .tab, and then it will show you all the functions you can call on that object. So it's not like Mathematica or Maple, where you just have a bunch of functions, and then you can get things as input, and you don't really, like, to know what you should do with the differential forms, like, I don't know. With this, what it has is, the same as Python in general, it's more object-oriented. You create an object, and there's a specific list of methods that you should call on it. And so it's not defined. You do question mark to see. Okay, form 1 dot exterior. Something that starts with an E. Yep, there is derivative. Yeah. Okay, let's try derivative. I might have to give the variable. Nope. Differential of a form does not take any arguments. Okay. Oh, that. There. How's that? That's better. Wrong way. That's great.
Do it again. See if you guys go.
Okay. I do.
All right.
I'm also curious if this works. Look at, there's another thing. I know this is tiny, but very, very nice feature of Sage is that almost every single thing in Sage has a, you can call LaTeX on it. It gives you back the thing to paste into your paper. And that's the sort of thing where we started with, oh, let's do it for rational numbers, integers. And then we're like, oh, let's do it for matrices, as long as the elements work. And then the things that involve matrices. And like, you basically just build your way up over many years, you end up having this work for almost everything. So that's the situation now. So that can be really handy to have. Okay, so back here. Oh, okay. So the point is, if you want to use Sage, and if you get past a certain hump, you might find that you really like the documentation a lot, because if you're like me, one of the ways you like to learn stuff, at least involving computation, is you want to see an example that actually works. You want to try it out and then vary it, because you know that you're basing what you're doing on something that's correct and actually works. And so in Sage, you just have a massive amount of actually working and tested examples. And that's kind of like your core documentation. Of course, there's other things, like there's a book, there's a book called Sage for Undergrads, which is kind of a nice narrative way. Yeah, there's a lounge copy of this book. It's called Sage for Undergraduates, and it's a very narrative approach to learning about Sage. So you read text rather than just trying examples. So I'll end with some weaknesses. I think non-commutative algebra is particularly weak in Sage, in my opinion. I wish it was. In other words, I really wish it wasn't. Algebraic curves and varieties. A lot of the algebraic geometry functionality is weaker in Sage than in background, and both speed and range of mobility. And this can get in your way depending on what you're doing. And it's really, really hard stuff to implement, and hasn't got really any movement at all the time. Whereas other things like geometry and topology have a huge amount of work done. I think if you're working with special functions, numerical stuff is really, really good in Sage, but symbolic things involving special functions can be pretty weak. You're shaking your head. You agree? Yeah. Yep. That's one of the working symbolically with special functions is a major strong point of Mathematica, and something that in Sage there's not really many people involved in Sage that care a lot about that, and it's really hard, just like some of these other things. So it is weak in Sage for sure. whereas the numerical parts are actually often very good. Another problem, depending on how you look at it, there are 1,657 known bugs right now in Sage. If you click on this link, the track server, which I showed you before, there's a query which is active bugs. Actually, when I wrote this, there are 1,657. I wrote this about an hour ago. Now there's 1,658. So unfortunately, the number is going up. But yeah, yeah, exactly. So there's that many known bugs, and I mean, some of them are really serious bugs. One of the bugs that one of the participants at the Sage Days is working on, or was working on yesterday, was computation of multifactorials. So it's like a basic function involving integers, and it was wrong. Like it would give you the wrong answer. And it was reported 7 years ago, and nobody fixed it. It was like an off by 1 year. And so that's really bad. And even worse, to really give you a caveat emptor link, this is a list of known bugs that silently produce wrong answers. So these are bugs in Sage where you ask it to do something and it just doesn't even give you a warning, doesn't raise an exception, doesn't say known issue, it just silently gives you the wrong answer. Actually, here's the multifactorial I was talking about. So that's obviously a very bad situation. So here's this one ticket. So it looks like 2 to the 64 dot multifactorial 2 to the 64. Maybe something doesn't work. That looks bad. 5 multifactorial 3 is Sage outputs 5, but it's supposed to be 10. Not good. So that's a really big problem with Sage. It's really big, and there are in fact some bugs. We did introduce something called stopgaps, which people should really do for all these tickets. And what they are is some extra bit of code that you add, so that if you try to use something that would produce the wrong answer, it's not silently producing a wrong answer. It will tell you that it's about to potentially give you a wrong answer. Right? So it might say multifactorial is known to have this bug. Here's a link to the ticket. Maybe the range you're using it on is fine. So that's better than nothing. It's something that one can quickly do. And that reduced this list quite a bit from what it was before. But I mean, it's bad that it's like this. On the other hand, Mathematica and Maple probably have a similar list. You just don't know what it is. So with that, I will conclude my talk and hope that somebody here might reduce the number of bugs. Or report more. Okay, so are there any questions? Yes?
So on this last thing, if you've got FPGA using Exec-C using Exec-C, and the bug appears in Exec-C, so the flags for the cat propagate.
The first thing to point out is with Sage, we have our own package system, and if package C acquires a bug, it doesn't in any way impact Sage until we update package C to a new version in the Sage distribution. So Sage is really a collection of specific versions of all of its dependencies, plus its own new code. And so we at least control our environment. It would be very hard if you have these bugs and you can only reproduce them when you happen to be using the version of a certain library on Linux, whereas when if you run Sage, say, on a certain version of Linux, it happens to use some version of some library and things break, but otherwise they don't break. So that would be incredibly hard to deal with. So Sage is kind of different than like image editing programs and stuff, where maybe like the result of a bug or some weird change somewhere else is that a pixel is slightly off. In Sage, you just get potentially mathematically very wrong answers. One very small change over here dramatically changes the output of something over there. And so, the point is just that Sage is a complete package, including all of its dependencies, even the compiler. So, I kid you not, one of the Sage packages, which is typically built as part of building Sage from source, is C, the GNU compiler collection, GCC. It checks to see what GCC you're building with, and if it's not a known good one, it will build its own copy of GCC and then continue to build using that. Because often we'll run into errors that are caused by the compiler, which you notice when doing mathematical things, but you might not otherwise notice or care about. So that may or may not answer your question. Maybe it didn't answer it at all. But the versions of A, B, and C are kind of well defined at least. That's all I'm trying to say. Which is a major problem. Usually with software, you just have your own library, and then you have kind of random versions up to some constraints of other software that are dependencies. In Sage, it's all 100% well defined, which makes things really hard.
If you run something and there's an error, what happens?
Well, yeah, so we know for example, multi-vector.
Yeah.
Okay, so somehow, I mean, that raises some doubts about, at some level,
Mhm.
about everything that goes into multi-factorial.
Yep.
And so the question is, how far back?
That's a very good question. Let me show you something. In this worksheet, let's look at, I want to show you how accessible the source code is. If I put double question mark
After a function name, then it shows you the source code of that function.
And in this case, the code is written in Cython, which is a compiled variant of Python. And here's the code of the multifactorial function. And so this is the code that contains a bug. If you look through it, I think you'll see that it doesn't call anything else except itself recursively. And maybe this subprod, oh no, that's just an array. It's pretty self-contained.
And the main thing it relies on is the GMP, the GNU Multi-Precision API, for manipulating large integers. So it's either buggy because this algorithm is implemented incorrectly, that's actually the case, or because there's a bug in GMP. And you'll know that pretty quickly because you're looking at the source code right here and now of that function. Okay. But it could have been that when we did double question mark and looked, instead of seeing a bunch of code like this, it could have been 2 or 3 lines that call into the Perry C library, for example. And if that would have been the case, then you're like, oh no, Perry's multifactorial is broken. I wonder what depends on it. And maybe there's lots of things in Perry that use it, and then other things are broken as a result. And at least now you can look through the Sage source code and see what calls this function, and wonder about what is broken as a result of this function being broken.
I think, by the way, that people typically consider multifactorials with a 2, and in practice, and that one works fine. It's only for certain bigger
Values as the input, that there's a problem.
Okay, other questions? Yep.
That's sort of related. If somebody becomes an expert in one of these other packages that Sage, that's under Sage umbrella,
Yep.
do you recommend to those users, well, try it in Sage because you might be using a much of, like say Gap, you may be
Yep.
using a much older version of Gap in Sage, right? I don't know if that's the case.
Not sure how to answer that.
I mean, there are a lot of nice things about Sage, the
Yeah.
interface, the ability to use it with LaTeX and all this stuff.
Mhm.
And sometimes I wonder when I'm using Gap, for example, in Sage,
Mhm.
what things I can depend on that I'm used to using when I just use Gap, and what things I shouldn't depend on. Like, I guess I have to go and look at what version it's using.
Yeah, it's just some version of Gap, probably the latest. If it isn't, maybe you're the guy that updates it.
So one of the points is there are optional packages. So Sage is already large, but for Gap in particular, there are at least 2 packages which install 20 or 50 additional Gap packages. So when you want to have the full Gap package inside Sage now, you install additional code, and then you can even call Sage-Gap to access everything that's there. So it's not like an okay layer at the time everything, but you can really use Gap directly from the
But it's pulling in its own version of all the
Yes.
packages,
Yes.
not your version of the package.
Yes.
Okay.
Well, you can install Gap packages that Sage will pick up if you set the right environment variable. So you can share packages between Sage's Gap and your own copy of Gap. If you want to.
So it's a closed environment, but
Yeah.
it's open in the sense that there is a Gap version that's provided by
Yeah.
this environment.
And by default, it won't touch, even if you install Gap packages locally, by default, it won't notice them.
Yeah.
You have to explicitly ask it to.
You can ask it what version of Gap it uses.
Yep.
You can even ask it, you can use a Gap console. I think even right here, if you just do percentage Gap, you
Yeah.
can simply use Gap.
Yeah, well, that's
Probably
I-
do.
I haven't done this in a while, but I remember kind of not knowing whether I should be
Gap
doing
version.
that and just trying to use Gap as is inside Sage, or I should try to use it as Python
Oh, you were
objects. It was kind of.
Oh, I know what you're asking now. Jeez. So I guess there's no gap.
Yeah, this is another aspect of my question: is should you use
Oh,
these
478.
gap things as Python objects with a dot
It de-
notation, or should you use the actual gap function?
It depends. So if you know Gap really well and just want to write your program into Gap, then that could be fine. But what if you need to combine something with something that Gap doesn't provide? For example, Gap isn't very good at floating point numbers. It's pretty bad at floating point numbers. So maybe you're doing some. Okay, here's a really concrete thing. I remember wanting to compute Bernoulli numbers using Gap. It was insanely slow because the best algorithm for computing Bernoulli numbers involves lots of floating point arithmetic. And so I was like, oh, that's kind of funny. So if you needed to compute something with big Bernoulli numbers, but you also want to do some stuff with Gap, maybe then you'd use Gap from Sage via.
What he means is the following. So we have a lot of different systems in Sage. I can make the number 2 in Gap. And I can also make the number 2 in Paris. And I can make the number 2 in Maxima, which is in Sage. I can make, oh, maybe I should use different letters. Maybe, what's another one I should use? Singular? Yeah. So these are all different number 2s, okay? Actually, pure Python. Every single one of these is different. So if I do type of A, type of B, type of, this is tedious. It'll print out a whole bunch of different data types. So one's a gap element, another one's a GP element. Oh, you reevaluate. A GP element, a maxima element, a singular element, a Sage integer, and a Python int. And you can then do stuff with this A, for example. You can do A plus A. Okay, 4, so 2 plus 2. But you could also combine it with, you could do A plus F. And it will convert it, and it will find some place in which to add these two together. That's just the number 2, but instead of that, you could replace 2 by a finite group or something like that. And then you could call methods on that through the Sage interface. And also one thing somewhat recent is the gap interface that's being used right there when you create 2 is actually, there's like, I want to see something, I want to see what's true about it. Don't actually know. There can be performance issues, so I'm just curious how long this takes. If that takes, so yeah, that takes about a millisecond. So it's doing a huge amount of stupid work in adding those two things, but we have a different interface to Gap and a different interface to Paris and so on. That's a C library interface, and then it's dramatically faster. And so if you can use that, then that works a lot better. This is clearly not that, because that's almost, I mean, that's a really long time to add 2 numbers. But let's see, I think it's called LiveGap. That's the C library interface. I'm not sure if that's the right. Yep. Now watch. So if I do type of X, it's a lot faster. See the difference? 500 microseconds versus 895 nanoseconds. So it's way faster. Around 1,000 times faster. So there's a lot of overhead if you do Gap with something, which completely disappears if you use this very C library interface, which, like a lot of things in Stage, has a long and painful history of development by multiple people, including me. It's really incredibly crazy but the point is there's one other aspect of Sage that I didn't really mention. It has all these other programs in it, and it's connected with all these other programs, and it allows you to create objects in all of those programs and use them together, which is something no other software does at nearly the same level. And it's done that for over 10 years. And so in some cases, especially if you know how to use it, it can be very, very efficient for doing that sort of thing. So,
That sort of thing documented.
yeah.
How would you know which call to do,
You ask for support. Yeah, there'll be like probably 50 pages. I don't know. There might be 20 pages about LiveGap. I don't know. But
Yeah, there will be examples, and you can do live gap question mark and stuff. But knowing that there's a gap thing and a live gap thing, and that one of them is 1,000 times faster than the other, that's it's not. Well, you guys all know now. And with GP, with Peri, which is a number theory library, similar to gap with the number theory, there's the slow one is called GP, and the fast one is called Peri. Not called live GP, which would make a lot more sense. But it has a similar situation where one is fast and one is slow. But the slow one is a little more flexible in that there's some things you can do with the slow one that you can't do with the fast one. Like you can run it on a remote computer and you can run multiple copies of it at once that are independent and stuff like that. So
And then you can also, with mark or like percentage GP or something, actually write the
yep, if you do %GP, you can then just write a Peri, Linit. You can just write Peri code. L global red E. Straight up 100% Peri code with syntax highlighting and auto indentation and stuff.
one thing I noticed that was fun, I think we maybe spoke in the course here with Fortran.
Oh yeah,
You
percent
have to write
Fortran.
Fortran.
I have no idea how to write anything meaningful in Fortran. I don't even know.
I don't know either.
I don't even know if that's a common approach. But yeah, but you have to do there's a bunch of boilerplate you did. But if you type Fortran question mark, you'll see what it is. So yeah, you can write a function in Fortran, and then it will what will happen is the function will then suddenly appear as something you can call from Python everywhere else in the worksheet. So all right, so definitely out of time. So thank you very much. Any other questions?